Hello and welcome to the lecture on nonlinear acoustics in imaging. Let's discuss linear versus nonlinear systems. So linearity is a property of a system or a medium in which waves are propagating, for example, in which the principle of superposition is satisfied. So for a nonlinear medium, the shape and amplitude of a signal at a location is not proportional to that at the input. So here is a schematic of a linear system. Let's assume that if this system has the input as xt, the output is x prime t. And if the input is yt, the output is y prime t. In that case, if I sum scaled versions of the input, the output will also be a scaled version. Now this property is not satisfied by a nonlinear system. So now nonlinear systems are more challenging to analyze. You may be familiar that linear systems can be analyzed using principles such as convolution, especially when they are time invariant or shift invariant, but that property does not apply for nonlinear systems. So now what's a nonlinear medium? A medium can behave as linear or nonlinear based on the applied acoustic pressure. Here we are talking in terms of acoustics. Now here is a plot where we are showing the change in density in the medium as a function of pressure. And what you see here is that beyond a certain threshold, the curve becomes nonlinear, right? So this is not surprising because almost all systems behave nonlinearly beyond certain inputs. So if the input increases beyond a certain threshold, typically the system starts behaving nonlinearly. So you may have heard sounds. For example, you may have bought cheap speakers which sound pretty good at low volumes, but when you increase the volume, you start getting that distortion, which is the nonlinearity. So similarly here, at low pressures, we see this linear behavior, but beyond it, we start seeing nonlinearity. So now what's a nonlinear medium? We define a parameter called beta, or the coefficient of nonlinearity, which denotes the strength of nonlinearity in the medium, how nonlinear the medium is. Now how do we get this beta? So if we consider the equation of state. In the previous lectures, you have heard Professor Carla Mercado-Shaker talk about the equation of state in the context of the derivation of the wave equation. So you will recall that the equation of state relates the changes in density in response to changes in pressure. So as the wave propagates, there are changes in pressure. How does the density of the medium change in response to those changes in pressure? Now if you take this equation of state and you write it as a power series, right, where the first term is going to be the linear term, then you will have the second order term, third order term, higher order terms. Then these constants a and b are the coefficients of the linear or the first order term and the second order term, which is the harmonic term. Now we can ignore higher order terms for now, and if we take a ratio of these and we add this constant 1 to it, then we define a new parameter beta, which actually incorporates both b and a. Then the higher the nonlinearity in the medium, the higher will be the harmonic component relative to the linear component. So this is a metric of how nonlinear the medium is going to be. Now here are the beta values for some different media which are relevant to us. For example, fat, liver, heart, blood, breast tissue, and what you see here is that the beta value is very high for fat, right? So we can expect fat to demonstrate higher nonlinearity. Now it is not quite as simple as that. We will discuss later through a parameter called Gol'dberg number, because there is another parameter or the attenuation which is also important. Nonetheless, let's proceed. So first of all, why does this nonlinearity occur? What is the source of this nonlinearity coming from the medium? Wouldn't it be nice if we were just to send the wave and it came out as a scaled version of the input? Well, it turns out that typically in linear acoustics, we assume that the perturbation caused by the wave propagation in the medium is really small, so that the medium properties are not really changing much. Any changes in density, for example, can be ignored. However, when we have high amplitude waves or even finite amplitude waves, what you can expect is that there will be density differences in tissue as the wave propagates, because we have this compression phase, right, and then we have a rarefaction phase. So here is an example where this is the compression phase, where the wave is actually going to compress the medium, and here is the rarefaction phase. So when the medium is compressed, the density increases, and when the medium is rarefied, the density decreases. So now if you recall, typically we say that the speed of sound, the longitudinal speed of sound, can be defined as the square root of the bulk modulus and the density. So B is the bulk modulus, I think Professor Karla has discussed this before, and rho is the density, right. But it turns out, if you have this medium that is changing, then both the bulk modulus and density will become variable. They won't stay constant. So here is an approximation of the speed of sound for such a medium. The speed of sound doesn't remain constant, but it becomes a function of the particle velocity. So the velocity with which the particles in the medium are actually oscillating, that affects the overall speed of sound at that point, right. So now what this will do is, in regions where the density is higher, you will get increased speed of sound, and in regions where it is lower or in rarefaction regions, you will have a decreased speed of sound. So now imagine that this is the wave, and in this part of the wave, you expect the speed of sound to increase, and in this part of the wave, you expect the speed of sound to decrease. So if these vectors denote the speed of sound, then you can see that this is a shorter vector, that means lower speed of sound, and this is higher speed of sound. So what do you expect? So now let's just observe this figure right here, which shows that in the compression phase, the speed of sound is faster, and in the rarefaction phase, the speed of sound is lower, because in the compression phase, the medium will get compressed, and in the rarefaction phase, the density will drop. So now what do you expect? This part of the wave will actually start gaining over this part of the wave. It will start moving forward, and this part will start getting left behind. So you start getting this distorted waveform, right. Now in the extreme case, as the waveform starts getting distorted, you reach this waveform, which is called a shock wave. Shock, because there is a sudden change. You can see there is a very sharp transition here. Typically when we say a shock wave, that is what we mean, that there is a very drastic transition in the pressures. Now as the wave starts getting distorted, let's look at the spectrum of the wave. What do you expect to happen? Initially, this is like a short sine burst, right. So it will be centered around a single frequency, f naught. But as the wave starts getting distorted, harmonics are getting added. So here are some harmonics, f naught, 2f naught, 3f naught. When it becomes a shock wave, a large number of harmonics will get added. Theoretically, to get a shock wave, you would need infinite number of harmonics, so that you will be able to create this kind of a shock wave. Now what happens after this wave propagates a very long distance, right? So these higher harmonics will start getting attenuated, because we know that attenuation is proportional to frequency, right? So like I said, the shock wave will become more and more nonlinear with distance, because as we move further, the wave starts getting more and more distorted, right? However, these higher frequencies now start attenuating very fast. So because of that, after a while, even if you provide more input, you are not gonna get more output, right? And then the higher frequencies start attenuating. So if you move further and further, eventually all the higher frequency components die out, and you get back a wave which loses its harmonic components. So now let's talk about this nonlinear propagation. Nonlinear propagation, because the nonlinearity builds as the wave propagates further, right? So nonlinear propagation increases with distance till saturation is reached. But once you have the saturation, right, the output is not going to increase even if you increase the input. Because any increase in energy that you are giving, the higher frequencies that are generated because of the nonlinear wave, or rather the distorted wave, will be very quickly absorbed. So that is what prevents the wave from becoming multi-valued. Like for example, you may be wondering, now this is a shock, but what is preventing the wave from becoming like this? Like for this point to move further this way. But if that was the case, the wave would become multi-valued. At a given time instant, there would be multiple values. But that doesn't happen because beyond the shock wave formation, you cannot have higher frequency generation because those higher frequencies are very rapidly attenuated. So moving on, I just want to make one more point, is that this nonlinear propagation is a different phenomena qualitatively and quantitatively from nonlinear scattering of bubbles that we have studied in cavitation, right? So both are nonlinear effects, but cavitation is different from nonlinear propagation, as we will see more. So here is an example of some data we captured in our lab. This is a pulse, relatively short pulse. This pulse has propagated a certain distance, and now initially this pulse was shaped like a sine wave. But now you see, if I look at the peak positive or the peak compressional pressure, then you will see that this is in voltage units. So it has not been converted to pressure, but nonetheless it's 0.2 units. Let's call it arbitrary units, 0.2. But if you look at the rarefractional phase, it is not even 0.15. So as you can see, there is asymmetry in the wave. The peak compressional pressure or peak compressional amplitude is more than the peak rarefractional amplitude. And this is somewhat characteristic of nonlinear propagation. Now, in diagnostic ultrasound, you don't get very extreme nonlinear propagation, shock waves, etc. But when it comes to therapeutic ultrasound, you get shock waves, and there are applications such as histotripsy, lithotripsy, where you get shock waves. But this is a moderately nonlinear wave, and this is more relevant to diagnostic ultrasound. Now, how do we analyze this nonlinearity? We can model. There are several models so that we can figure out what these beams do. So one model is called the second order Westervelt equation. Here we are talking about the lossless Westervelt equation. So this is the P is the pressure, instantaneous pressure. C naught is the, if you remember, we had written dz by dt equal to C naught plus beta u. If you remember this equation, that's the beta term there and that's the C naught term, and rho naught is the equilibrium density. Because the density is changing, you are getting compressions, you are getting rarefactions, but the mean density is going to be rho naught. So this can be modified if you have an additional term related to viscous absorption. Then you can get this term where again this alpha naught relates to the absorption or the attenuation coefficient. Like I had said, typically absorption is the primary part of the attenuation. Therefore, sometimes it's harder to measure absorption and easier to measure attenuation. Sometimes we go with the attenuation coefficient and we call it absorption coefficient because they're approximately similar. Now this equation is harder to solve. The Westervelt equation is harder to solve, computationally more intensive. So there is a simplification which uses an approximation, and this equation is called the Kokolov-Zablotskaya-Kuznetsov or the KZK equation. It was formulated by a group of Soviet scientists, and this equation is simpler to solve, and it accounts for nonlinearity, diffraction and absorption. It largely is accurate along the axis of the beam, assumes a circular transducer. It's not very accurate beyond the axis. So for example, if this is the transducer face, then this is your axis. So it's most accurate on the axis. But like I said, it's easier to solve. And there is a package called HIFU simulator, HIFU standing for high intensity focused ultrasound, which is a MATLAB based program. You can download it, it's freely available, and you can use it to simulate these kind of nonlinear beams. So now let's talk about Gol'dberg number, which I mentioned in the beginning of the lecture. So first let's define this parameter called normalized distance nonlinearity parameter, or sigma. Sigma is beta times epsilon k z. Z is the distance that you are traveling, z or z is the distance that you are traveling. Epsilon is the acoustic Mach number. So you may have heard of Mach 1, Mach 2, Mach 3. So Mach relates to the speed relative to the speed of sound, right? So you may have heard of a fighter jet going at Mach 1 or Mach 2. So here this Mach number relates to the speed of the particle relative to the wave speed. So u naught by c naught, right? This is the Mach number, and a higher Mach number is going to lead to higher nonlinearity. So beta, as you see saw in the previous slides, beta is 1 plus b by 2a. K is the wave number, 2 pi by lambda, and z is the distance, like I mentioned. So as the wave propagates, it experiences nonlinear propagation, but after a point, it starts getting attenuated, the pressure reduces, and since nonlinearity is proportional to the pressure, then the wave will reach a stage which is called old age, in which the harmonic components are mostly attenuated and the wave starts looking sinusoidal again. But there is another aspect to it. A medium may have a strong nonlinearity, propensity to be nonlinear, right, as dictated by the nonlinearity parameter, but the medium may also have very high attenuation. So these are two competing effects. The nonlinearity metric is suggesting that a lot of harmonics will be generated, but the attenuation is suggesting that they will also be attenuated rapidly. So these two competing parameters will decide how distorted a wave gets, right? If you have, say, moderate nonlinearity but very high attenuation, the wave is not going to distort much because attenuation is going to very quickly dissipate the high harmonics. So to understand whether or not a medium will show significant nonlinearity, a parameter called Gol'dberg's number was created, where it is a ratio of the nonlinearity growth term divided by attenuation coefficient times distance. So sigma divided by alpha z, and as you know what sigma is, so you can get this form. Now when this Gol'dberg number becomes 1, then you start getting shock or nonlinear distortion. So here are some Gol'dberg numbers of certain tissues in the body, and these were tabulated at 5 megahertz frequencies and for 5 megapascal amplitude of the ultrasound wave. So what you see here is for breast tissue, Gol'dberg number is less than 14, liver less than 14, blood it's about 14, but for water it's 266. So this is very interesting because water is not a very attenuating medium. So even though the nonlinearity is not that high, because it is not an attenuating medium, effectively the amount of distortion that the wave sees is much more than in water than compared to all these other tissues. So now let's start thinking about the properties of these nonlinear beams. So if a wave distorts, what kind of an ultrasound beam results and how we can exploit it for our benefit. So it turns out that if you look at the beam, you can decompose the beam into the fundamental frequency f naught at which the transmission was made, and you can also filter out f naught and you will be left with the higher harmonics, or let's say you could look at the second harmonic of the beam or the third harmonic. So For these harmonic signals, it turns out the wavelength is less because higher frequency, speed of sound remains the same, c equal to f times lambda. If you apply that, you will see that if frequency doubles, lambda becomes half. And we also discussed that as you focus the beam, the lateral resolution is limited by the wavelength. But now the wavelength itself is reducing, so the beam becomes narrower and narrower, right? As the beam becomes narrower, the main lobe width reduces, and because of which, if you do imaging, you can get better resolution. More on that later, but here's the formula for beam width. If you remember, this is a simplified formula, lambda times axial distance by aperture diameter. This is just after the Fresnel region, right? So reduced lambda is actually going to give you narrower beam width. So like I said, if you have a thinner beam or a narrower beam, you will get better lateral resolution. Now, if you have narrower beams, that means the main lobe of the beam is narrower. But as you know, if you have a finite size transducer, you are also going to generate some side lobes. So it turns out that as you go higher and higher in frequencies, the side lobes are more. Okay, but they are much lower in amplitude. And also, because these beams, they are pressure dependent, right? Wherever you have high pressure, that's where these harmonics, higher harmonics are generated. So these side lobes are weak in pressure, so they don't really generate much signal. Therefore, these beams have relatively weak side lobe levels, which is great for imaging because it actually creates a natural apodization effect. We discussed earlier that in apodization, we provide weights to the transducer array so that you have a smooth pattern of particle velocity variation along the surface of the transducer array. But here, that is happening naturally because the side lobes are getting suppressed anyways. So now how can we exploit it? There is something called tissue harmonic imaging, which is used very frequently in cardiac and some deeper abdominal imaging. So tissue generates harmonic components, and when you receive the echoes, as long as your transducer is sensitive to this harmonic component, let's assume the transducer bandwidth allows you to measure some harmonics as well along with the fundamental. So both the fundamental and the harmonic is being captured. Now we can do some processing and we can eliminate the fundamental frequency so that only the harmonic frequency remains. So now the image that we can create with these harmonic frequencies is called harmonic image. For example, a second harmonic image. So what's the benefit? So it turns out that these images will have better resolution, better lateral resolution like I said, because of higher frequency, right? At the same time, lower side lobe levels. So anyways, here is the process which is shown schematically. Initially, you fire at a particular frequency. It's not going to be with a very high Q factor transducer, so it's a range of frequencies. Now, as the wave propagates in the medium, you start getting these harmonics. Let us say of these harmonics, the strongest component is 2f0. So I am going to filter the 2f0 component and I am going to now have a harmonic beam and I am going to make an image out of this. So now how do I isolate this harmonic signal? One way is to use a filter, but there are other ways as well. Sometimes it's hard with filtering because you may need a very high order filter to separate these fundamental and harmonics, because there may be some overlap, spectral overlap, because we use relatively broadband signals. Now this could be the fundamental beam frequency and this could be the harmonic beam frequency. So there is some spectral overlap, and that's where the filtering will not do a great job. So there are these methods which we have discussed in contrast enhanced imaging previously. One method of pulse inversion, in which you send, if you send two pulses in succession and then they propagate in tissue, and after some time you sum these pulses. The only thing is these pulses were initially inverted in phase. So if you sum up the input, you get the answer as 0. But now, because of the principle of superposition, if you sum up the output, the answer is also going to be 0, right? So, by doing this, we can eliminate any linear components. Any fundamental components will be eliminated and the nonlinear components will remain, which is shown in this schematic, that if you have the distorted wave now with the fundamental and harmonic components, if you sum it up, the fundamental component will be largely suppressed, but the harmonic component remains, and this is an efficient way of extracting these harmonics. So, like I said, nonetheless, there should be minimum overlap between the transmit and receive frequency to limit noise and to limit clutter. So, in some cases, pulse inversion does better than filtering, right? When there is some overlap, then filters don't do a great job, but pulse inversion does a good job. So, now let's talk about this power modulation in more detail. So, here if you have the input that has a relationship that the amplitude here is twice the amplitude here, right. So, now if I scale this waveform by a factor of 2 and subtract from this waveform, I am going to get an answer of 0. Now, as this is a linear system, even in the output, this relationship will hold. Let us say the input had an amplitude of A and the output had an amplitude of A prime, and here the input had the amplitude of A by 2, then the output should have the amplitude of A by 2 prime. And therefore, if I scale the output here by 2 and subtract from this output, under linear systems, I am going to get almost 0 output. Theoretically, it will be 0, but practically because of some motion, etc., you are not going to get exact cancellation. So, because of physiological motion, for example, some time is elapsed between the capturing of these pulses, and therefore, there may not be exact cancellation, but more or less the signal is suppressed. But here, if we consider nonlinear medium, so tissue is a nonlinear medium under this framework where we are dealing with finite amplitude waves. So, now this scaling property is not going to work. So, even after you scale the output by 2 and subtract, there will be a residual nonlinear signal, and this is essentially the harmonic signal that you are capturing. So, these are clever methods of isolating the nonlinear signal. Now, let us talk about attenuation of nonlinear beams. Like I mentioned, higher frequency is attenuated faster, because if you remember, attenuation follows a power law relationship with frequency. So, higher the frequency, higher the attenuation, and these harmonics will undergo higher attenuation. But what is the physical consequence? The physical consequence is the absorption is higher now because of these higher frequency components, and that will lead to a temperature increase. So, when we are dealing with nonlinear beams, there can be high temperature increase. So, this is important from the safety point of view, but also it is useful when we talk about high intensity focused ultrasound surgery, because these high frequency beams have a very high absorption, and that leads to a very rapid temperature increase, which leads to the destruction of targeted tissue by thermal necrosis. So, here is an example of tissue harmonic imaging. This is probably not the best example I have seen, but nonetheless, if you see, there are some features here in this fundamental image, which was taken at f0, and it is more clearly visible. The boundaries here are better visible. Some parts are invisible here, which are better visible here, and the image in general looks sharper. So, in tissue harmonic imaging, we get higher resolution due to a narrower beam width or the higher frequency that is generated. So, a natural question might be, why not just use a frequency which is higher? Why do we need to rely on this tissue harmonic imaging to generate frequencies which are higher? And it turns out that tissue harmonic imaging has better penetration depth compared to fundamental imaging at double the frequency. Why would that be the case? Because if let's draw this out here. So, imagine that this is your tissue and you send a beam. If you send a beam which is at high frequency, let us say 2f0 to begin with, it starts getting attenuated right here, okay. But consider generating this beam through the nonlinear propagation. It's still getting developed. The nonlinear signal is growing in this phase. Okay? So now if it scatters from a target and it comes back, only in the receiving mode or only in the path back, it will experience high attenuation. The beam which is transmitted is an F0 beam, the received beam is 2F0 frequency beam. So, I mean this is an approximation, but nonetheless what you see is that there will be lower attenuation here compared to if I simply use 2F0 frequencies. I hope that makes sense. So, that is what is written here, that higher attenuation is experienced only for half the distance for the echo signal. While going, you do not experience that much attenuation because the nonlinear signal is developing, it is growing as the distance increases. Also, like I said, you will have more side lobes with harmonic imaging, but lower side lobes because the side lobes are weak. And when we are imaging at higher frequencies, right, if it was just 2F0, it would have more but lower side lobes. But when we generate this 2F0 frequency with nonlinearity or nonlinear propagation, then because the side lobe pressure is very weak, so you do not really generate very strong side lobes. So there is an additional advantage right there. So like I said, we are getting this 2F0 signal. Now you may ask why 2F0, why not 3F0, 4F0? Well, it turns out there is some bandwidth limitations which we will discuss in a later slide. So 2F0 or harmonic imaging is the most popular. Now if you have lower side lobes, you are going to get reduced clutter, you will get sharper images, you will get better resolution because of narrower beams, and you will get better contrast because of lower side lobe levels. So like I mentioned earlier, this is used for cardiac and abdominal and other deeper organs. The only challenge here is the harmonic signal typically is weaker than the fundamental signal, several dB down relative to the fundamental signal. So the signal to noise ratio can be a challenge, but nowadays with sensitive electronics, we trade off the signal to noise ratio to get better contrast, better resolution, and still improve imaging performance. So now let us discuss what kind of transducers are needed for harmonic imaging or tissue harmonic imaging. You would need transducers that are sensitive to both the transmit frequency as well as receive frequency. So for example, if I am sending the signal at F0 and now the received signal is at 2F0, then my transducer has to be sensitive at F0 as well as 2F0. So if it is a very narrow band transducer such as the one shown here, if this is F0, let us say here is F0 frequency, this is F0, 2F0 will be beyond the bandwidth of this transducer, so it cannot be used. But if I have somewhat broadband transducer, I can fire at F0 on the lower edge of the bandwidth, and then on the higher edge of the bandwidth I can capture 2F0. So this is how there is a more stronger constraint in terms of bandwidth requirements when you are going to do tissue harmonic imaging. So like I have written here, for harmonic imaging, transducers should be broadband to accommodate both the transmit and receive frequencies. In some cases, two different elements are used, one for transmit, one for receive, and one is sensitive at F0, which is used for transmit, and the other one is sensitive for 2F0, which is used for receive. So like I said in the previous slide, there is a more stringent bandwidth criteria. You have to have a transmit bandwidth which is contained in the transducer bandwidth, as well as the receive bandwidth should also be contained in the transducer bandwidth. And there is some overlap here, that is inevitable, but that is usually taken care of by techniques such as pulse inversion or power modulation. They are able to still separate the linear and nonlinear frequency components. So typically we use a broadband array transducer, or in some cases researchers have reported coaxially placed multiple transducers where the one element serves for transmit and the other element serves for receiving the signal, which is shown in this schematic. So you are sending the signal with F0 or rather you are sending the signal with f0 using this outer element, and the inner element you are receiving the signal at 2 f0. So these crystals are designed to be sensitive to f0 and 2 f0 respectively. Now, contrast agents have been discussed in a prior lecture, and so like we have discussed, contrast agent exhibit significant nonlinear behavior due to a different mechanism because of their volumetric oscillations in which they oscillate nonlinearly, and here we are talking about the nonlinearity caused by nonlinear propagation. So cavitating contrast agents also scatter ultrasound at frequencies that are harmonics, right? And this is what is called stable cavitation, and they are detected for contrast specific imaging. So there is a mode which is called second harmonic imaging in which 2f0 is used. But now consider if you have some tissue where there is some blood vessel here and there are contrast agents here. So now this contrast agent will give you harmonic signal at 2f0. But you have a tissue which is also acting as a nonlinear medium here, tissue, and this tissue is also giving you signal at 2f0. So now the harmonic from the contrast agent will become confounded because of the harmonic from tissue. So I will write tissue, and this is ultrasound contrast agent. So if I use higher pressures for imaging, I will get significant tissue harmonic, because of which I will not be able to get good imaging performance in detecting these bubbles, because the background signal will also be present. So in other ways, the 2f0 frequency is not going to be very specific to the bubbles. So at low pressures, when the tissue harmonic is weak and the bubble oscillations show moderate nonlinearity, you can still get an improvement with these bubbles. But at higher pressures, you are not going to get an improvement because of strong tissue harmonic generation. So researchers have looked at another mode called the subharmonic imaging, in which you don't look at f0 frequency or 2f0 frequency, but f0 by 2 frequency. You preferentially isolate and visualize these subharmonic frequencies, and it turns out that subharmonic signal is not generated in tissue harmonic imaging, because tissue harmonics, the mechanism through which tissue harmonics are generated, primarily harmonics are generated and not subharmonics. Therefore, if the transmission is done at f0, but the image is created using either subharmonic at f0 by 2 or nf0 by 2 with higher order n's generating what you call as ultra harmonics, then these frequencies are specific to bubbles. They are not generated significantly through nonlinear propagation. So now you can still have your tissue with bubbles. The bubbles are giving out subharmonics or ultra harmonics, and the tissue is not. So therefore you can very clearly separate the bubble region from the tissue region. So that is the benefit of subharmonic imaging. But the main challenge with subharmonic imaging is that it is a threshold phenomena. You have to exceed a certain pressure threshold. Only then you start getting these subharmonics. And sometimes when you are doing subharmonic imaging, there is also a chance of bubble disruption because of the higher pressures that are needed for subharmonic imaging. Well, so to conclude this lecture, let us just summarize what we have learned. We learnt about sources of nonlinearity in ultrasound, and cavitation being one and nonlinear propagation is the other. We also learnt about the absorption of nonlinear beams, how the higher frequencies generated by these beams will be absorbed more. This can lead to temperature elevation. We discussed how nonlinear beams can improve the performance because of better resolution of these beams, also because of lower side lobes, which leads to lower clutter and better contrast. We discussed the hardware and signal processing considerations, especially related to transducer bandwidth and how we can separate out these harmonic signals by suppressing the fundamental signal. And lastly, we contrasted, if I can use the pun, we contrasted how nonlinear acoustics is different from contrast agents. So with this, I think we will conclude this lecture. and I'll see you in the next lecture. Thank you.